Okay, good? So far, so good? Yeah. Okay, now that we have found the gravitational force at the surface of the Earth, I want to calculate the gravitational variation if I go up and if I go down. How do I do that? So I know we just calculate G at the surface equals 9.8 meters per second squared. We just did that. Now I want to see what happens if I go up. Variation of G with altitude and with depth. So suppose I call altitude X and depth D. So we calculated that our G at the surface was given by G mass of the Earth divided by the radius of the Earth squared. Now what happens when I go up? So my 0 is my reference point. And first of all, I'm going to increase my altitude. And I'm going to call my increase in altitude X. As I go up, will my G change? Will I be able to now write G mass of the Earth divided by R radius of the Earth plus X squared? Now I have to compare. I'm going to call this equation 0. And I'm going to call this equation 1. So now I have to figure out how much variation is there in G with altitude. May I write this? If I have to compare, is that how we compare things? May I change the division sign so it becomes GME over RE plus X squared times RE squared over G mass of the Earth? May I get rid of these two? May I take RE common out from this? May I get rid of these two? Am I left with 1 plus X over RE to the minus 2? Is this GX over G still? Okay, so far so good? Since we have a minus 2 in the numerator, may I use binomial expansion? Binomial expansion. 1 plus X to the power minus N is approximately equals minus NX. And then there's more terms, n minus 1 over 2 factorial x plus blah, 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 x squared. But if x is small, we can ignore all of the other terms. So then this means, may I rewrite this as 1 minus 2x over RE? This only works when x is much, much smaller than RE, right? And this term is tiny. Everybody knows about binomial expansions, right? No? Somebody said no. Okay, so binomial expansions, every time you have that's a good question. Okay, so let me explain this. When you have this term, which is very tiny, why is it tiny? Because no matter how big you make your x, it will be smaller than RE. So any number 1 over 1,000, even if it's like 1,000 times less than the Earth, what is this number? 0.001, right? It is a tiny number. In a situation like this, you can use binomial expansion when your next term is small. And the way you use your binomial expansion is this way. You take the power, you put it next to it, and you're done. And yes, the binomial expansion actually doesn't stop here. I believe the next term in it is n minus 1 over 2 factorial x squared plus 3 factorial plus 4 plus 5 and so on. But if x is tiny, what is x squared?
Super tiny.
Super tiny. What is x cubed? Super, super tiny. What is x to the power 4? Super, 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 super tiny, right? So you ignore all the terms that are to come. Does that make sense? That is the reasoning why you could use binomial expansions. Yes, sir?
When we say like when x the number is...
It all depends on context. So for example, in case of this, it could be 10,000 meters. That would be considered tiny. Whereas if you were talking about a scale like a meter scale, then probably a millimeter or a micrometer would be very small. So it all depends on reference point. It's all relative. So if you're talking of the distance between the sun and the earth, the distance to the moon is tiny. If you're talking about how far Oort cloud is from the sun, the distance between the earth and the sun is tiny. But yes, that's a good question. So it's all relative. So it depends on what context you're talking about. Okay? This means gx over g equals that. Or may I write this as g minus 2x over reg? What does this equation say to you? This was our g at the surface. This is our new g. We are subtracting this factor from our value of g. So this equation should read to you that the g at altitude x has been reduced by the factor 2x over re. So, how do we say this? Gx has been reduced from g at the surface. Woohoo!